Welcome back to Science, to Sleep By, where the universe becomes your quiet companion, and every mystery drifts gently into your imagination. Tonight, we're taking a peaceful journey far beyond the warm glow of the sun, past the orbits of the giant planets, past the drifting comets, and even past the place where the solar wind slows to a whisper. Beyond that soft, dim horizon lies a region so distant, so untouched, that light from the sun takes months, even years, to reach it. A realm where space grows colder, quieter, and older, carrying secrets that astronomers are only beginning to understand. In this calm, unhurried exploration, we'll travel to the outermost edges of our cosmic neighborhood. We'll listen to the gentle stories of the Oort Cloud, the distant wanderers that visit us from interstellar space, and the strange gravitational hints that something unseen may be moving in the darkness. So settle in, breathe deeply, and let your thoughts drift outward like starlight. Because tonight, we're going to explore what might be hiding beyond our solar system. This is Something Strange is Hiding Beyond Our Solar System, a slow-paced celestial journey meant to help you unwind, imagine, and fall asleep with the stars. At the far edge of our solar system, beyond the reach of familiar planets and well-mapped orbits, there lies a boundary unlike any other, a threshold between the world we know and an unknown realm that stretches into the quiet forever of interstellar space. This region, often imagined as a dim and distant horizon, is not a sharp line or a solid wall. Instead, it is a slow fade, a place where light weakens, warmth dissolves, and the comforting influence of the sun becomes soft enough to feel like a memory. For scientists, this frontier is not only a physical boundary, but a conceptual invitation, a calm whisper that encourages deeper questions about our place in the universe and the forces shaping everything we see. As we drift in thought toward this distant frontier, imagine the gentle glow of sunlight that brightens the skies of Earth, slowly thinning as you move past Jupiter, Saturn, Uranus, and Neptune. Out here, the sun is no longer a blazing disk in the sky, but a bright star among many, its power diminished, yet still guiding the invisible currents of the heliosphere. The heliosphere, a vast bubble of solar wind that stretches billions of miles in every direction, forms the protective cocoon around our solar system. It shields us from cosmic radiation and interstellar particles, creating a calm interior environment where planets and moons follow their stable paths. But at the boundary of this bubble, where solar particles lose their strength, space becomes a different place, altogether harsher, quieter, and more ancient. Scientists call this boundary the heliopause, and it represents one of the most mysterious regions of the solar system. Only two human-made objects, Voyager 1 and Voyager 2, have ever crossed it. These spacecraft, now drifting through interstellar darkness, have sent back signals revealing a cosmic frontier more complex and puzzling than anyone expected. Instead of a simple transition, the edge of the heliosphere seems to shift, compress, ripple, and pulse, responding to solar cycles, magnetic storms, and perhaps even structures in the interstellar medium itself. These changes suggest that something dynamic and uncharted may be influencing the solar system from beyond its outermost layers, something that challenges ideas of emptiness and silence. For astronomers, the strangeness of this region is not just about the heliopause. It is about the entire boundary zone that leads up to it. This area includes the Kuiper Belt, where icy dwarf planets drift in elongated orbits, the scattered disk, where gravitationally disturbed worlds move with unpredictable energy, and the theoretical inner Oort Cloud, a distant reservoir of frozen remnants that may extend thousands of times farther from the sun than Earth does. Together, these structures form a multi-layered shell of debris, mystery, and barely understood motion. Each layer hints at processes that occurred during the earliest days of the solar system, collisions, migrations, and gravitational battles that sculpted the worlds we know today. Yet even with large telescopes, powerful observatories, and deep space probes, the far frontier remains incredibly difficult to study. Objects out there are small, dark, and slow-moving, often reflecting so little sunlight that they become invisible long before our instruments can detect them. Their orbits stretch over such vast distances that it can take centuries to trace even a fraction of their paths. The gravitational pull of the Sun is weak at those distances, allowing external forces passing stars, galactic tides, and clouds of interstellar dust to subtly influence the motion of these distant bodies. Because of these shifting forces, astronomers suspect that the outer frontier is not merely empty space, but a dynamic arena shaped by interactions we can barely measure. In recent years, patterns observed in the orbits of remote objects have sparked new conversations about what might be hiding beyond the planetary region. Some bodies appear to tilt in the same direction, cluster in similar pathways, or move as though shepherded by an unseen mass. These unusual alignments have raised the possibility that our solar system may not be as solitary as it seems. Whether this hidden influence comes from a distant planet, a cluster of dark material, or a gravitational pattern created by the galaxy itself remains uncertain. But the very fact that something could be out there just beyond the reach of direct observation adds a quiet, compelling depth to the mystery of the frontier. For the U.S. scientific community, the edge of the solar system represents one of the final unexplored territories within reach of our technology. Missions like Voyager were made possible because of American innovation, engineering, and curiosity. And future interstellar probes are now being designed with the hope of mapping the outer regions in greater detail. These missions aim to move faster, travel farther, and record data more precisely, perhaps even reaching the Oort Cloud within a human lifetime. Such endeavors draw from a long tradition of exploration, echoing the spirit that once carried ships across oceans and aircraft across skies. Now, that spirit looks upward, toward the unseen distances where our solar system fades into the galaxy. As our understanding deepens, the cosmic frontier becomes more than a distant location. It becomes a reflective space for the imagination. It is a place where the known dissolves into the unknown, where the structure of the solar system blends into the structure of the universe, and where every unanswered question gently invites another layer of curiosity. The frontier beyond our solar system is not defined by noise or activity, but by quietness, by subtle forces, and by the soft presence of possibilities waiting to be uncovered beyond the familiar planets. Past the drifting comets of the Kuiper Belt and the scattered icy worlds that orbit at the edge of our sun's influence, lies one of the most extraordinary and mysterious structures in our cosmic neighborhood. It is not a planet, nor a star, nor a region of glowing gas, but a vast, nearly incomprehensible sphere of icy bodies surrounding the solar system like a delicate halo. This region is known as the Oort Cloud, and its existence transforms the way we imagine our place in the universe. Instead of a small cluster of planets isolated in the darkness, the solar system becomes a shimmering island wrapped in a quiet sphere of ancient, frozen material that has existed since the very beginning. The Oort Cloud is believed to stretch from tens of billions to possibly a trillion miles beyond the Sun, a distance so immense that the human mind naturally struggles to picture it. While the planets lie in a flat, disk-like arrangement, the Oort Cloud forms a truly three-dimensional bubble around the solar system, extending in every direction. If the solar system were the size of a coin, the Oort Cloud would be the size of a football field surrounding it. And yet, despite its staggering size, it is composed mainly of small icy, comet-like bodies, each one so far apart from the next that they could drift for thousands of miles without ever coming close to another object. This distant, frozen reservoir is thought to be a remnant of the solar system's earliest years, a time when the sun was still forming and planets were battling for space. In that chaotic era, countless icy objects were kicked outward by the gravitational influence of giant planets like Jupiter and Saturn. Instead of being ejected entirely from the solar system, many of these early fragments settled into extremely long, slow orbits that carried them far into the darkness. Over millions of years, these icy bodies formed a spherical cloud, bound to the sun by only the faintest gravitational thread. Today, the Oort Cloud is a kind of time capsule, preserving materials from the dawn of our planetary neighborhood. For scientists, the Oort cloud is both fascinating and frustrating. It is too far away for telescopes to study directly, too faint to reflect enough sunlight for easy detection, and too vast for spacecraft to reach using current technology. Everything we know about it comes from indirect observations, primarily from long-period comets that fall toward the Sun from its outer shell. These comets appear in the sky with little warning, arriving from random directions, often taking thousands or even millions of years to complete a single orbit. Their unpredictable paths, enormous distances, and immense ages all point to a shared origin in the Oort cloud. The behavior of these long-period comets gives astronomers valuable clues about the structure of the cloud itself. When a distant star passes near the solar system, or when the system drifts through dense regions of interstellar space, gravitational nudges can disturb the fragile balance of the Oort cloud. Even a small shift in gravity can dislodge a comet, sending it slowly inward on a long path toward the Sun. When these icy wanderers finally reach the inner solar system, their surfaces warm, creating bright tails of dust and vapor that stretch across the night sky. These quiet, luminous visitors remind us of the invisible sphere of ancient material surrounding the Sun, a sphere that rarely reveals itself but always waits in the darkness. The Oort cloud's vastness also suggests that the solar system is not as isolated as it seems. Its outer regions lie so far from the Sun that they begin to blend with the gravitational environment of the galaxy itself. This means that the Oort cloud is shaped not only by the Sun, but also by passing stars, drifting molecular clouds, and the subtle tidal forces generated by the Milky Way. Every few million years, a nearby star may pass close enough to tug on the outermost comets, altering their positions. These gentle pulls can change the cloud's shape, redistribute its objects, or even send a cluster of comets inward together. Over billions of years, these galactic influences continually reshape the Oort cloud, making it a dynamic structure quietly sculpted by both solar and cosmic forces. For scientists in the United States and around the world, the Oort cloud represents one of the final untouched territories of the solar system. Because it is so remote and so difficult to study, it remains a place defined more by mystery than by observation. Yet it is also a region full of scientific promise. The icy bodies within it may contain pristine materials from the early solar system, molecules and minerals that never melted, never collided, and never changed since their formation. These fragile objects could help scientists understand how the Sun formed, how planets emerged, and how water-rich bodies were delivered to worlds like Earth. As research continues, new theories suggest that the Oort cloud may not simply be a peaceful halo of icy fragments, but perhaps a record of encounters with other stars in the Sun's birth cluster. Some scientists believe that a portion of the Oort cloud's material may have come from other young stars forming in the same region as the Sun. In that scenario, our solar system would not be entirely self-contained, but part of a larger cosmic story, one that includes the exchange of material between neighboring stars in their earliest years. This possibility adds a gentle and poetic depth to the idea of the Oort cloud, turning it into a cosmic archive of interactions stretching back more than 4 billion years. Despite its invisibility, the Oort cloud plays an important role in shaping how humanity imagines the outer solar system. It emphasizes that the Sun's domain is not limited to planets and moons, but extends far into a quiet realm of darkness, where icy relics drift undisturbed. It reminds us that the solar system is a broad and layered structure, with each region telling a different story about time, gravity, and the slow evolution of celestial bodies. And it invites both scientists and dreamers to consider what else might be hiding beyond that faint, icy frontier, waiting for future explorers to uncover it in the quiet expanse beyond our solar system, where darkness stretches unbroken for trillions of miles. Countless objects drift freely between the stars. They travel without allegiance to any sun, without the companionship of planets, and without the predictable orbits that shape life within our own cosmic neighborhood. For most of human history, these wanderers remained hidden, too faint and too distant to detect. But in recent years, A new chapter in astronomy opened when a few of these mysterious travelers drifted close enough for us to notice. Their arrivals were brief, subtle, and almost easy to miss, yet they delivered a message that continues to reshape our understanding of what lies beyond the solar system's boundaries. These interstellar visitors offered a rare glimpse into the deeper galaxy, carrying clues about faraway star systems and the strange conditions that might exist in the broader cosmic landscape. The first of these visitors was a small, elongated object detected in 2017 and named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. Its discovery marked a milestone in astronomy. It was the very first object ever confirmed to come from outside our solar system. When telescopes first captured its faint signal, astronomers noticed something unusual. Unlike comets or asteroids within our system, which follow long but predictable orbital paths, Oumuamua was moving too fast to be gravitationally bound to the Sun. Its trajectory traced a hyperbolic curve, a path that indicated it had arrived from interstellar space, passed quickly through the solar system, and was heading back out into the galaxy. What made Oumuamua even more intriguing was its shape and behavior. Measurements suggested it was either extremely elongated, like a thin, tumbling shard, or perhaps flattened like a pancake. None of the familiar objects within our solar system resembled it. Even more puzzling, Oumuamua seemed to accelerate slightly as it moved away from the Sun. Normally, this is something comets do when they heat up and release gas, producing a faint push. But telescopes detected no tail, no gas, and no visible outgassing of any kind. It behaved like a comet without looking like one, and like an asteroid without following expected patterns. For scientists, this combination of characteristics challenged everything they thought they knew about small bodies in space. Because of these uncertainties, Oumuamua became a scientific mystery that encouraged a wide range of explanations. Some researchers suggested that it might be made of exotic ices that evaporate invisibly. Others proposed that it could be a fragment of a larger body torn apart by tidal forces near a distant star. A few more imaginative theories speculated that it might even be artificial, though no evidence supported that idea. What mattered most was not the speculation, but the realization that objects like Oumuamua were far more diverse than anyone had predicted. Its brief appearance hinted at the possibility that the galaxy is full of unusual fragments shaped in environments unlike anything found near the Sun. Just 2 years later, another interstellar visitor approached our solar system, this time with far clearer features. Named Borisov, it was discovered in 2019 by an amateur astronomer and quickly confirmed to be the second known interstellar object. Unlike Oumuamua, Borisov behaved exactly like a normal comet, showing a visible tail, a coma of dust and gas, and a chemical composition that could be studied in detail. Its approach was slower, its features brighter, and its structure far more typical. But what made Borisov extraordinary was not its appearance, but its origin. Scientists analyzing its composition found that it contained higher levels of carbon monoxide than any comet from our solar system. This suggested it had formed in a much colder environment, perhaps in the outer reaches of a distant planetary system orbiting another star. This discovery offered something remarkable, the first direct evidence of the chemical makeup of another planetary system's building blocks. Borisov acted like a cosmic message in a bottle, carrying ancient materials from a faraway region of the galaxy directly into our neighborhood. Its presence showed that comet formation is not unique to our solar system, and that the processes shaping small icy bodies are universal across the Milky Way. It also hinted that the diversity of objects drifting between the stars may be vast, each one shaped by the environment of the star it once orbited. The arrival of 2 interstellar objects in such a short time raised an important question: how many more are out there, drifting unseen? For decades, scientists believed interstellar objects were extremely rare, but the detection of Oumuamua and Borisov suggested that they may be far more common than previously thought. Some models now estimate that millions of such objects could be passing through the solar system every year, invisible to telescopes because they are too small or too dark. This means our solar system is not an isolated island, but part of a bustling cosmic sea where fragments from other stars travel freely through interstellar space. These visitors also provide insights into the forces acting on the solar system from the outside. The fact that interstellar objects can enter and exit the solar system so easily indicates that our boundaries are permeable, shaped by gravity, but open to interactions with the galaxy. Each passing fragment brings with it the fingerprints of stellar environments that may be hotter, colder, denser, or older than our own. By studying them even briefly, astronomers can gather clues about how planetary systems evolve, what kinds of materials they contain, and how common the conditions for life might be elsewhere in the galaxy. For the United States, the study of interstellar objects has become an area of growing scientific investment. NASA has begun planning potential missions to intercept future interstellar visitors, with designs that include rapid response spacecraft ready to launch on short notice. These missions would attempt to reach incoming objects before they pass too quickly to study. Capturing close-range data from an interstellar visitor could reveal details about its surface, composition, structure, and origin information that would otherwise be lost forever. Such a mission would be a landmark achievement, opening the door to the first direct exploration of material from another star system. As astronomers continue searching the skies, each interstellar object serves as a gentle reminder that the galaxy is full of movement and connection. The solar system is not a closed space, but part of a larger network shaped by drifting fragments, gravitational influences, and ancient materials traveling over unimaginable distances. These visitors, silent and fleeting, give us a window into that larger universe, showing us that something strange and wonderful may be hiding beyond the boundaries of our familiar world, waiting to be noticed as it drifts through the quiet darkness between the stars at the farthest reaches of our solar system, where sunlight fades into a faint glow and the gravitational pull of the sun weakens to a gentle tug. There is a region filled with small icy bodies following long and lonely orbits. These distant objects drift through the outer Kuiper belt and the scattered disk, moving so slowly that their position barely changes over the course of a human lifetime. And yet, despite their remoteness, these faint wanderers have revealed something that has captured the imagination of astronomers across the United States and around the world. They appear to be responding to a hidden influence, an unseen gravitational presence tugging at their orbits, shaping their paths, and whispering the possibility that a massive world may be hiding in the cold darkness far beyond Neptune. This idea, known as Planet 9, is one of the most intriguing scientific mysteries of our time. It began not with direct observation, but with patterned small, subtle alignments in the orbits of distant objects that seem too orderly to be random. Astronomers noticed that some of these bodies, instead of spreading evenly around the sun as expected, appeared to cluster in similar directions. Their orbits tilted in related ways, their paths elongated along shared angles, and their alignment persisted even as new objects were discovered. After years of careful examination, scientists proposed that these unusual orbits could be explained by the gravitational pull of a large, undiscovered planet orbiting far beyond the known planets. If such a planet exists, it would likely be several times more massive than Earth, perhaps 5 to 10 Earth masses, and orbit the Sun at an astonishing distance, maybe 10 to 20 times farther out than Neptune. At that distance, a single orbit could take between 10,000 and 20,000 years to complete. A world like this would not be a bright, easily spotted object, but a dim, slow-moving point of light, lost in the vastness of space and invisible to most telescopes. It would be colder than any known planet, with a surface temperature far below the freezing point of any material found on Earth. If it has an atmosphere, it might consist of faint traces of hydrogen, helium, or methane, forming a thin envelope around an icy or rocky core. The planet would be ancient, serene, and drifting through a region where almost nothing else resides. What makes the Planet 9 hypothesis especially compelling is the consistency of the orbital evidence. When scientists simulate the solar system without this hidden world, the orbits of the distant objects gradually scatter into random directions. But when they include a massive, distant planet in their models, the clustering reappears. The objects behave just as the real ones do, tilted, elongated, and aligned. It is as if the outer solar system is whispering the presence of a massive guardian, one that guides the motion of small bodies, like a conductor guiding the soft notes of an orchestra. The idea fits not just some of the observations, but many of them, making it one of the most persuasive explanations for the strange orbital patterns observed far from the Sun. Yet, despite this mathematical confidence, no telescope has directly observed Planet 9. Its possible location covers a wide swath of sky, and because it is so distant, it could appear thousands of times fainter than Pluto. Even the most powerful ground-based telescopes must scan slowly and patiently, sifting through countless stars and galaxies to find a single faint, moving point. The planet might be hiding in a region of the sky dense with background stars, making it nearly impossible to distinguish from distant galaxies. It might also lie in a part of the sky that many telescopes have only begun to explore. Finding it requires not just powerful instruments, but careful strategy, persistence, and a willingness to search inch by inch through the coldest, darkest corner of the solar system. The search for Planet 9 has energized the scientific community, inspiring collaborations among observatories across the United States and beyond. Powerful telescopes like the Subaru telescope in Hawaii, and future facilities like the Vera C. Rubin Observatory in Chile are being used to map the sky with unprecedented sensitivity. These observatories are capable of detecting even the faintest moving objects, making them ideal tools for the hunt. The Vera C. Rubin Observatory, in particular, will repeatedly scan the entire southern sky, capturing billions of objects and allowing astronomers to identify slow-moving bodies that might have been overlooked. Many expect that if Planet 9 exists, this new generation of telescopes may finally reveal it. The idea of a hidden planet also connects to the history of planetary discovery in the United States. In the 19th century, astronomers predicted the existence of Neptune based on disturbances in Uranus's orbit, and their calculations proved correct. In the 20th century, Pluto was discovered after decades of searching for a suspected Planet X, though it turned out to be much smaller than expected. These discoveries reflect a tradition of using careful measurements and patient observation to uncover new worlds. The search for Planet 9 carries that tradition forward, blending modern technology with the timeless curiosity that drives scientists to explore the unknown. Beyond scientific interest, the possibility of Planet 9 reshapes how we imagine the solar system. It suggests that our planetary family might be larger and more complex than previously thought, with faraway members drifting in darkness, influencing the motions of objects closer to the Sun. It adds depth to the story of how the solar system formed, hinting that interactions with the early Sun or with passing stars may have placed a massive planet on a distant, elongated orbit. It also suggests that the outer regions of the solar system are not empty, but filled with gravitational patterns, invisible structures, and slow cosmic dances that unfold across tens of thousands of years. The search for this hidden world reminds us that even in an age of advanced technology, space still holds vast mysteries. The solar system, once thought to be fully mapped, now reveals new layers of complexity that encourage scientists to question assumptions and look more deeply. Whether Planet 9 is eventually found, or whether another explanation emerges for the orbital patterns, the investigation itself expands our understanding of the forces acting on the outer solar system. It opens the door to new theories, new explorations, and new ways of thinking about our place in the galaxy. In the quiet darkness beyond Neptune, where the Sun's influence becomes a gentle memory, something appears to be guiding the motion of distant icy bodies. Something massive, distant, and unseen, shaping orbits with a gravitational hand too soft to feel, but too consistent to ignore. And somewhere in that vast darkness, a world may be waiting, drifting silently at the edge of the solar system, holding clues about the history of our cosmic home and the unseen depths that lie beyond it. At the distant boundary where our solar system meets the vast openness of the galaxy, a faint curtain of energy marks the final reach of the sun's influence. This boundary, known as the heliosphere's edge, is not a clear or solid structure, but a shifting, rippling frontier shaped by the solar wind and the surrounding interstellar environment. It is a place where particles slow, magnetic fields twist, and the steady stream of energy flowing outward from the sun begins to collide with the raw material of the galaxy. For decades, scientists imagined this region as a simple transition from solar space to interstellar space. But when humanity's first deep space explorers Voyager 1 and Voyager 2 arrived there, they discovered something far stranger, something that challenged long-held assumptions and revealed that the outer boundary of the solar system is one of the most mysterious regions we have ever encountered: the solar wind. A constant stream of charged particles flowing outward from the sun creates a sort of bubble around the solar system. Inside this bubble, the sun's magnetic field and energy dominate the environment. Outside it, the environment belongs to the galaxy. For a long time, astronomers believed the edge of this bubble was relatively smooth, a gentle slowdown of solar particles until they faded into the interstellar medium. But when the Voyagers reached this region more than 11 billion miles from Earth, they found a far more complicated and energetic frontier than anyone had predicted. Voyager 1 reached the edge first, entering what scientists call the heliosphere, a turbulent zone where the solar wind slows dramatically as it pushes against the interstellar medium. This region turned out to be filled with strange signals. Particle counts fluctuated in unpredictable ways, magnetic fields pulsed with unusual rhythms, and radiation levels spiked in patterns that defied earlier models. Instead of a smooth transition, the spacecraft found a chaotic, energetic environment, a kind of cosmic weather system as complex as anything on Earth. Voyager 2, reaching the region years later, confirmed these findings. The data from both spacecraft revealed that the heliosphere's boundary was not uniform but varied by location, shaped by the movement of the solar wind, the influence of interstellar magnetic fields, and perhaps even by structures farther out in space. One of the most surprising discoveries was the sudden drop in solar particles, paired with the dramatic increase in cosmic rays. Once the spacecraft crossed the heliopause, the true outer boundary of the heliosphere, this point marks the moment when solar particles no longer dominate the environment and interstellar particles take over. The transition was expected, but the abruptness and intensity of the shift startled scientists. In just a short distance, Voyager went from a region where solar energy shaped the environment to one where cosmic radiation from distant stars and supernova became the primary influence. The data suggested that the boundary acted almost like a membrane, allowing certain particles through while blocking others in unexpected ways. Equally puzzling were the magnetic field readings. When Voyager 1 entered interstellar space, scientists expected to see a clear rotation in the magnetic field direction as it shifted from the sun's field to the galaxy's. Instead, the direction barely changed. This suggested that the heliosphere and interstellar magnetic fields might be aligned in a way that no model had predicted, or that the transition region was far more complex than previously understood. Voyager 2E's readings provided additional data, but the magnetic mystery remains a subject of intense study. The outer boundary of the solar system seems to be shaped by forces that scientists are only beginning to understand. The energy variations near the heliopause also raise new questions. Some researchers noticed that the region seemed to contain layer shells of different temperatures, densities, and particle intensities. Instead of a single boundary, the heliosphere's edge might consist of multiple nested layers that shift over time as the sun's activity cycles rise and fall. During periods of high solar activity, the solar wind strengthens, pushing the boundary farther out. During quieter periods, the boundary contracts. This suggests that the solar system breathes, expanding and shrinking over decades in response to the sun's changing behavior. In addition to these dynamic processes, the region appears to contain pockets of anomalous energy, localized bursts of energetic particles that neither the solar wind nor the interstellar medium fully explains. These bursts could be the result of magnetic reconnection, a process where magnetic fields break and reconnect, releasing energy, or they might be caused by interactions between solar particles and interstellar dust clouds. Some theories even suggest that the solar system periodically encounters clumps of interstellar material regions where dust, gas, or even dark matter is denser than expected. If the heliosphere moves through such a region, it could alter the shape of the boundary and influence the patterns detected by spacecraft. For scientists in the United States, these discoveries represent a major milestone in understanding how the solar system interacts with the galaxy. The Voyager missions, launched in 1977, have become some of the most significant scientific endeavors in American history. Their journey into interstellar space has given humanity its first direct measurements of the conditions outside the solar system. No other spacecraft has traveled so far or revealed so much about the environment beyond the sun's reach. The data they send back, though faint and slow, continues to provide insights into magnetic fields, cosmic radiation, and the behavior of charged particles at the boundary between solar and interstellar space. These findings also have important implications for future missions. If the solar system's boundary is more active and complex than expected, spacecraft designed to explore interstellar space will need to withstand varying levels of radiation and unpredictable particle environments. Engineers are already designing new interstellar probes that can reach the heliopause faster, travel farther, and collect more detailed data than Voyager ever could. These missions could help map the shape of the heliosphere, determine how often it encounters energetic regions of the galaxy, and reveal whether the environment beyond the sun's influence holds additional surprises. What makes this region so compelling is that it represents the solar system's final frontier, the outermost edge of the sun's domain, before the universe transitions into the broader environment of the galaxy. It is a place where two vast systems meet, the solar system with its warm, dynamic core, and the interstellar medium with its ancient, cold currents drifting between stars. The energies that flow through this boundary shape the solar system's protective bubble, shielding planets like Earth from high-energy particles that might otherwise be harmful. Understanding this boundary helps scientists better understand the forces that have shaped our world and will continue to influence it as the solar system moves through the Milky Way. The strange energies detected by Voyager remind us that even at the edge of what we know, the universe remains full of surprises. The heliosphere's boundary is not a simple border but a living, changing region where forces from the sun and the galaxy collide in quiet but powerful ways. It is a zone shaped by magnetic tension, cosmic particles, and the delicate balance between solar and interstellar winds. And as our spacecraft continue their slow journey outward, sending back whispers of data from billions of miles away, the story of this mysterious frontier continues to unfold. When astronomers first detected an object moving through our solar system back in 2017, an object later named Oumuamua, they realized something extraordinary. The strange, elongated traveler was not from our solar system at all. It came from the deep, cold stretches of space far beyond the sun's influence, and as quietly as it arrived, it slipped back into the darkness, leaving behind far more questions than answers. But what made this event even more fascinating was that it wasn't just a one-time occurrence. A few years later, another interstellar visitor, Comet Borisov, drifted into our cosmic neighborhood. Unlike Oumuamua, which behaved unlike anything we had ever seen, Borisov looked much more like a typical comet, except that it wasn't from here. It came from an entirely different star system, carrying with it the chemical fingerprints of a world that formed under a different sun. These visitors are reminders that our solar system isn't isolated or sealed off. Space is open, shared, and constantly exchanging pieces of itself across unimaginable distances, but beyond the ones we've detected. Scientists believe countless more interstellar objects pass through our solar system silently, invisibly unnoticed. Most are too small, too dark, or too faint for our telescopes to detect. They drift like cosmic dust motes floating through an endless, dimly lit room. Our sun's gravity gently nudges some of them, pulling them into long arcs that curve gracefully before flinging them back into interstellar space. Others simply pass through, unaffected, like strangers walking past us in a crowded, darkened hallway. And somewhere out there far beyond where our instruments currently reach lie the origins of these mysterious travelers. They may come from planetary systems that no longer exist, torn apart by supernova or collisions. Some may be remnants of worlds that formed billions of years before Earth, and some may even be fragments of planets still orbiting distant stars, carrying material that once sat beneath alien sunsets. Imagine, for a moment, one of these silent wanderers gliding through space. No engine, no direction, no spark of life aboard. Just a cold, ancient piece of cosmic stone or ice that has spent millions, or even billions, of years drifting between the stars. Between each journey, between each star system, it experiences nothing but darkness, radiation, and the slow erosion of time. It's easy to forget that these objects are not merely rocks. They are records. They carry within them frozen minerals and chemical traces that preserve the conditions of their birthplaces. They hold clues about the atmospheres, temperatures, and chemical soup that once swirled around distant suns. When such an object enters our solar system, it's almost like receiving a message. Not in words, but in composition, a snapshot of an environment billions of miles and billions of years away. What makes this even more captivating for scientists is how these interstellar visitors reveal the dynamic, interconnected nature of the galaxy. Stars are not isolated islands. They form in clusters that drift apart. Their planets fling debris into interstellar space during their early chaotic years. Stellar flybys disrupt the orbits of comets and asteroids. And gravitational nudges from massive planets can launch small objects outward like slingshots. These effects create a galaxy filled with drifting fragments, each one on a path shaped by the physics of countless stellar interactions. So when one of these fragments enters our solar system, it carries the fingerprints of those ancient and distant processes. It's the galaxy reaching across unimaginable distances and brushing lightly against our home. Yet for all we've detected, there's still so much we don't know. Our telescopes are improving, but space is vast. And these visitors are tiny. They appear suddenly, travel fast, and often leave before we can gather much data. By the time we lock onto them, they're already halfway back into the void. This limitation has created an air of mystery. These objects could be natural or artificial, simple or complex, typical or completely unprecedented. Oumuamua, for example, showed no visible comet tail, no gas emissions, no orbit consistent with normal space rocks. It accelerated in a way that puzzled scientists. Some proposed exotic explanations, while others insisted it must be a natural but unfamiliar type of object. The truth is, we don't yet know, and that uncertainty adds to the sense of wonder surrounding these interstellar visitors. As we look farther into the cosmos, we're beginning to realize that these passers-by may be more common than we thought. Our galaxy could be filled with them. Some estimates suggest that for every one we detect, tens of millions slip past undetected. That means that in any given moment right now, at this very instant, countless interstellar objects could be drifting through the darkness, just beyond the edges of our detection range. Some may be the size of skyscrapers, others may be no larger than pebbles, and some may move so silently and so invisibly that they will forever remain unknown to us. Yet they are there, sharing space with the planets and comets of our solar system, crossing through our gravitational field like faint whispers in the night. What makes this idea even more peaceful is the slow, timeless nature of their movement. These objects aren't rushing. They aren't hurrying. They drift with the soft, unhurried rhythm of the cosmos itself. Their journeys take millions of years, and their paths cross countless star systems. They don't belong to any one place. They are travelers in the purest sense, forever moving, never settling, and always carrying with them the quiet stories of the stars that shaped them. And when they pass us, we get a brief glimpse into a world far beyond our own. A world we may never visit, but can study for a moment before it slips back into the dark, What lies beyond our solar system becomes a little more mysterious each time one of these visitors appears. They remind us that the universe is full of motion, full of exchanges, full of hidden connections. They suggest that the boundaries we imagine around our solar system are nothing more than gentle transitions, permeable and open. And they hint at the possibility that what we see, what we detect, is only a fraction of what truly exists. Far beyond the familiar planets, beyond the Kuiper Belt's icy scattered ring, and even beyond the vast, nearly empty expanse where the sun's magnetic breath finally fades, astronomers have noticed something subtle, something quiet, something they cannot yet fully explain. It's not a light, or a sound, or a visible object. It's a gentle tug, a gravitational whisper coming from the darkness. Something faint, persistent, and strangely consistent seems to be pulling on the farthest objects in our solar system. And though the evidence remains delicate and incomplete, it hints that something large or something strange could be hiding in the outermost shadows of our cosmic neighborhood. This mystery began to unfold when astronomers studied the orbits of a handful of distant icy bodies known as trans-Neptunian objects. These small frozen worlds, drifting far beyond Pluto, follow paths that should be scattered randomly across the sky. After all, at such distances, the sun's influence weakens, and the gravitational forces acting on them should be dominated mainly by chance encounters and chaotic interactions. But instead, something unexpected appeared. These distant objects weren't scattered randomly, they were clustered. They seemed to be leaning in the same direction, as if influenced by a shared gravitational shepherd. Their orbits were elongated in similar ways. Their perihelia, the points where they come closest to the sun, were strangely aligned. And the odds of this happening by random chance were astonishingly small. As more of these distant bodies were discovered, the pattern deepened. It wasn't just one coincidence. It was a repeated, quiet signal carved into the architecture of their orbits. Astronomers began to suspect that something massive, something several times heavier than Earth, might be lurking far beyond Pluto's orbit, tugging on these distant icy worlds with a slow but steady pull. This hypothetical object became known as Planet 9. But this was no ordinary planet. If it exists, it would orbit the sun at a staggering distance, hundreds of times farther than Earth. One full orbit could take more than 10,000 years. Its light would be so dim that it would be nearly invisible, even with the most advanced telescopes. It would move so slowly across the sky that it could blend into the background like a silent ghost. Yet the gravitational evidence remains compelling. The orbits of these distant bodies behave as though something unseen is sculpting their paths. Not dramatically, not aggressively, but with a patient, ancient touch, like a gentle hand rearranging pebbles on a riverbed over thousands of years. And so astronomers continue to look. They scan the sky, mapping the motions of distant icy fragments, trying to pick out the tiny shifts that betray the presence of something large and hidden. But even as Planet 9 remains a possibility, other explanations emerge too. Some scientists propose that instead of one large object, there could be many small ones, perhaps a previously unseen cluster of icy mini-worlds whose combined gravity creates the illusion of a single massive body. Others suggest that the strange orbital patterns might be caused by the general gravitational influence of the galaxy itself. Even the passing of other stars, millions of years ago, could have gently nudged these distant objects into their current arrangement. The outer solar system is a dynamic place, influenced not only by the sun, but also by the slow tides of the Milky Way. Yet, the idea of Planet 9 continues to capture attention, not only because of the orbital anomalies, but because it fits into the broader story of how planetary systems form. When stars and planets are born from swirling disks of dust and gas, objects often get flung outward during those chaotic early years. Giant planets can eject smaller ones. Gravitational interactions can hurl worlds into far-flung orbits that take them to the cosmic frontier. In this sense, a planet wandering far beyond Pluto is not unusual, it's almost expected. Other star systems have shown us planets orbiting at incredible distances from their suns. Some are giants drifting in the cold outskirts of their systems. Others are rogue planets without a star at all. So if a distant planet exists here, It might simply be one of the many hidden by the darkness. Some researchers even contemplate more exotic possibilities. What if the unseen gravitational tug is not a planet at all, but something even stranger, like a tiny primordial black hole left over from the earliest moments of the universe? These hypothetical objects would be extraordinarily dense, incredibly small, and nearly impossible to detect directly, but their gravity would still be strong enough to tug on distant icy bodies. While this explanation remains speculative, it's an intriguing reminder that the cosmos may hold objects we have yet to imagine fully. As scientists refine their models and gather more data, the puzzle becomes clearer, yet remains unsolved. Telescopes around the world and in orbit search for the faintest motion against the starfield, trying to catch a glimpse of whatever might be hiding out there. The Vera Rubin Observatory, once fully operational, may be able to detect such a slow-moving and distant object. But for now, the mystery persists, wrapped in cold shadows and vast distances. It's the kind of puzzle that could take decades to unravel. Yet every new discovery, from the orbit of a distant object to the slight wobble in a comet's path, adds another clue. What makes this mystery so visually soothing and mentally calming is its sheer scale. We're not dealing with fast events or urgent changes. We're dealing with motions that unfold over millennia, forces that act gently, paths shaped by gravity, moving at a pace slower than the growth of mountains on Earth. These distant bodies don't rush. Their orbits stretch across time itself, and whatever is pulling on them, planet, cluster, or something stranger, does so with the softest touch, barely perceptible, yet incredibly persistent. The solar system, even at its furthest boundaries, is a place of slow, ancient motions. Everything drifts, everything glides, everything follows paths shaped by gravity's quiet hand. As the outer solar system continues to reveal its secrets, the possibility of something large and undiscovered lingering in the shadows becomes a reminder of how much lies beyond our reach. We tend to think of space as empty, but the gravitational fingerprints left behind suggest there's more out there, something shaping the darkness, influencing the edges, guiding the forgotten debris of planetary formation. Something that, for now, we can feel only through its pull, like a presence sensed but not seen. When we imagine the edge of the solar system, it's tempting to picture a sharp boundary, some cosmic border where the sun's influence simply ends and interstellar space begins. But in reality, the transition is far more subtle, far more gradual, and far more mysterious than any clear line could ever describe. The outer edge of our solar system is not a wall, it is a frontier, a vast, quiet, layered region filled with drifting ice, ancient relics, and the faintest traces of the sun's fading power. It is a place where space becomes unimaginably cold, where time stretches across billions of years, and where objects older than Earth itself continue their silent journeys through an ocean of darkness. This frontier is neither fully ours nor fully part of the galaxy beyond. It is a boundary zone, a twilight region between two worlds, the realm of the sun and the deep, interstellar medium that lies beyond. To understand this mysterious frontier, we have to imagine stepping outward from the familiar planets, past Neptune's windswept orbit, past the scattered bodies of the Kuiper Belt, and beyond the realm of dwarf planets like Eris and Makemake. Beyond even these distant worlds lies the heliopause, a delicate, ghost-like surface where the solar wind slows to a stop. Here, the charged particles streaming from the sun no longer dominate. Instead, the pressure of the galaxy takes over. The heliopause marks the boundary where our star's influence ends, but it is only the first of many layers. If you drift outward through this region, the faint glow of the sun dims until it becomes just another star, still familiar, still warm by memory, but no longer the commanding force. It is closer to home. The space beyond is not truly empty. The galaxy seeps into it radiation, particles, drifting dust, and the soft tidal pull of the Milky Way's enormous mass. This is interstellar space, a realm shaped not by one star, but by countless stars acting together. Their combined gravity forms a gentle, persistent background force. Their winds mingle, their radiation hums in the distance, and their ancient explosions scatter atoms across the galaxy like the slow settling of invisible snowfall for billions of years. Our solar system has sailed through this medium, orbiting the center of the Milky Way like a ship at sea. During that voyage, it has passed through interstellar clouds, dust lanes, and regions shaped by ancient supernovae. Some of these encounters may have stirred the objects on the solar system's fringes, sending waves of disruption into the outermost reservoirs of ice. Others may have stripped away or reshaped portions of the heliosphere, and some may even have delivered new material dust, particles, or dormant molecules that drifted inward over time. In this sense, the boundary of the solar system is not a wall but a membrane, thin and permeable, through which the galaxy and the sun gently exchange matter and energy. It is in this boundary region that astronomers suspect the Oort Cloud resides, an enormous spherical shell of icy debris that surrounds the solar system like a fragile, invisible cocoon. Its existence is inferred, but not yet directly observed, as the objects within it are far too small and too distant to detect with present instruments. Yet the evidence for the Oort Cloud appears in the long-period comets that occasionally glide into the inner solar system. These icy visitors arrive from distances so vast they defy ordinary comprehension. Some begin their journey from more than a light-year away, taking millions of years to complete a single orbit. Will we recognize the warning not as fear, but as invitation, the universe asking us to listen, to learn, and to remember that we are part of something vast, mysterious, and still unfolding? Imagine the stillness of space, the endless quiet where sound cannot travel, where motion itself seems suspended in time. There, under the faint warmth of the sun, 3I Atlas drifts. Its path, uncertain yet deliberate, loops through an invisible web of gravity that binds it to the solar system. It no longer races past like a visitor, nor does it fall inward to destruction. It simply moves, patient and slow, caught between freedom and captivity. This image for AVI Loeb becomes more than an astronomical event. It becomes a metaphor, a mirror reflecting the fragility of human understanding and the limits of our perception. 3I Atlas, in its silent orbit, is not just a physical body. It is a symbol of how humanity moves through the universe, curious yet confined, intelligent yet unsure of what it truly knows. The silence surrounding 3I Atlas is not only literal, but philosophical. Across the expanse of scientific debate, there is an almost sacred quiet when it comes to mysteries like this. Many scientists prefer to let such questions fade, and willing to dwell on uncertainties that lack immediate proof. Loeb, however, insists that this silence says more about us than about the universe. The cosmos speaks constantly, not through words, but through motion, radiation, and time. Every object, every photon, is a message. When we choose not to listen, when we dismiss anomalies because they make us uncomfortable, we lose the very essence of scientific inquiry. 3I Atlas, then, becomes an unintentional teacher. Its persistence within our sun's grasp urges us to confront the uneasy truth that science, like the orbit it studies, is circular. It returns again and again to the same question: what are we missing? In the context of a U.S. audience, this theme resonates deeply with the legacy of American exploration. From the pioneers who crossed unknown frontiers to the astronauts who stepped onto the moon, the American spirit has always been defined by curiosity mixed with vulnerability. Loeb's reflection on 3I Atlas taps into that same energy, the belief that progress comes not from certainty, but from daring to question the unknown. To gaze up at the sky and wonder what 3I Atlas's rock, relic, or probe is to participate in that lineage of discovery. The silence of space is not emptiness, it is invitation. And so, as 3I Atlas continues its slow, unending path, it embodies the paradox of existence itself. It is a traveler that has stopped traveling, a visitor that has become a resident, a mystery that refuses resolution. Its orbit is steady, but our understanding of it is not. It reminds us that science, like life, is a journey without a final destination. Every orbit leads to another. Every answer opens a new question. Every moment of silence contains a hidden echo of meaning waiting to be heard.